Zoom is also live? No.
It's the fifth Sunday of the month, 11 o'clock, and it's time for Chai and One. This, of course, is an online only session from the ultra cold atoms, ions, and molecules lab at TNFR. And before we go there, let me say that there's a lot of fun stuff happening at TIFR and at Chai and Y over the next few weeks. So, Monday, tomorrow, at 2 o'clock, we have a visit of the Director General of CERN, Mark Thompson, and he's going to be talking about a special colloquium on particle physics, present and future. And that's going to be followed by a very special screening of a film by CERN called The Peace Particle, of the history of CERN over 70 years and how this experiment has become a haven to get people from all around the world to collaborate on science. So do come for that if you can. It's at TIFR tomorrow. The first Sunday of September at Prithvi Theatre, it's going to be about physics of the plug point. And we're going to talk about how power comes at a plug point and some very interesting things that we perhaps never think about when we plug something into a socket. But today, it's time for ultra cold atoms. And with me is Professor Saurav Datta, who leads this group. And Saurav, how cold are these atoms?
So they are typically below 1 millikelvin. So
below 1 milli-Kelvin means
yeah.
Near absolute zero.
Absolutely.
Wow.
Yeah.
Wow. Should we go in the lab?
Yeah.
Okay. Let's go in the lab and see what's happening. Okay.
Here.
Oh wow! All your students are here.
Yeah.
They seem to be all excited to show us the lab.
Yeah.
Oh, let's lots of optics, lasers, power supplies, lots of fun stuff here. Okay. Why don't you introduce people to us?
Okay, so let me start. So here, this is Sushanta Barwan. He's a postdoc in my lab. This is Rahul Mohanty. He's a PhD student. And over here we have Satyavrata Vaidya, who is also another PhD student. And this is Ranjan Haldar, who is just very new in our lab. So, I guess they will give you a tour of the lab. So before
that, can you tell us a little bit about what your lab does?
Yeah.
So, I mean, something about, how do you make these cold atoms? I mean, I'm sure they will tell us the details and show us what's going on, but maybe some overview of what your lab does?
Yeah, so let me do that. So, what we do is we work with atoms and molecules, which basically make up everything, but we work with atoms and molecules in vapor phase. So they are very dilute systems where you actually can think of individual atoms moving around and molecules moving around. And by moving around, what you mean is that they have some speed or some velocity and some momentum. So classically, they will be moving with some momentum and some kinetic energy. But if you start cooling them down, what you essentially mean is that you are reducing the kinetic energy, which is basically reducing the speed of the system. So if you become cold enough, the interesting things happen. So there is this, some of you might know that there is quantum mechanics, which says that for a particle can also is described as a wave, and the wavelength of the particle is given by this lambda, which goes inversely as the momentum. So if this momentum is reduced, which means if the temperature gets colder, the wavelength becomes smaller. So if you reduce the temperature at some point, this is a particle, but the wavelength actually starts of this particle, which is called the de Broglie wavelength, it becomes visible. And if you go further, the wavelength increases even further. And if you go even colder, and you see that the notion of the particle becomes ill-defined, and you see this wavelength now tend to overlap. And this is an interesting regime where actually you have to think of physics in a different way, where you have to think about interacting, system interacting due to this overlap of the wavelength. And this is what my lab does. So we go very cold and we get rid of all the kinetic energy of the system. And we are basically only dominated by whatever remaining potential energy is there. So to do all these things, we actually have to start with laser cooling, which is what all my team will explain to you. And these are tremendous sort of good fundamental physics implications, and also, for example, applications. For example, in quantum sensing, such as magnetic field sensing or RF field sensing, and also in atomic clocks. So all these applications, which directly my lab does not work on clock, for example, but they all start with this laser cooling which has a lot of components going in. So I'll hand it over to my team, and they will slowly start explaining step by step how we get these laser cool panels. Okay, so I think Sushanto, you are taking over now. Yeah. Okay, Sushant, and you need the mic. Yeah. Hi, this is Sushanto. So today I will explain the saturated absorption spectroscopy setup that we use in our laboratory and to get the real atomic formation frequencies. And we use this laser to stabilize. We use these frequencies to stabilize our laser and use them in our laser cooling experiments. So as we know, atom has a nucleus and electrons move around this nucleus in certain shells. And these shells have discrete energy levels. For example, we can see the energy level of cesium. So let us focus here, this energy level diagram. Let us focus our camera here to the energy level diagram of cesium. So we have this ground state, 6s half. This is the ground state of cesium. And one of the excited state is 6p3/2. Right. So cesium is actually simpler atom because it has only one single electron in the outer shell, and that is why the energy level becomes more simpler. So now, is the energy level similar to that of hydrogen? Because hydrogen also has only one electron in the shell. Yes, it will be similar, but the splitting, the further splitting, that will that will differ. Yeah. Okay. So these energy levels actually splits into closely spaced energy levels. So because of the coupling of electron angular momentum with the nucleus spin. So we can see this ground state actually splits into two, and this excited state splits into four sublevels. So now, if we shine laser on the cesium atom, then what will happen?
So there is a question online. Why do you use atoms like cesium?
Yes.
Why not, hydrogen, helium, simple atoms? Why cesium, which is such a big one?
So we can use like any atoms, like which are in the alkali atoms. So in the group one of in our periodic table. So we choose cesium because we in our experiment we want cool cesium. So we can use like lithium, potassium, rubidium, francium, any of them. So we have chosen this because we are trying to in the further experiment we are trying to cool cesium.
So is cesium easier to cool than, say, sodium or potassium or something, or it's because it's more reactive, right?
Yes.
It will be difficult to handle cesium.
Yes.
Or you have very little bits of it. You don't
So we have very little. The pressure is very lower, 10 to the power minus 12. So it is very low compared to the atmospheric pressure. So yes, we use lithium also in the other setup. So that will be explained by.
So you can cool all these atoms. You can
Yes.
cool all these atoms.
Alkali atoms.
Alkali atoms.
Yes. Okay. They have simple energy diagram and they have like cyclic transition. So that helps in laser cooling.
Okay. So these atoms are chosen because they're easy to cool with a laser.
Yes. Thank you. Thank you. So now, if we shine laser to the cesium atom, so what can happen? So this cesium atom can absorb laser photons and go to the excited state. But there is a catch. The frequency of the laser should match to the energy difference of this diagram. Right. So from this absorption, actually, we can measure the transition frequency. Right. So if we change the frequency of the laser, and we can see at specific frequency, the atom will absorb laser photon and it will go to the excited state. And we can measure the spectrum experimentally. Now, let us move to the schematic diagram of our system. So we have a laser here and some laser controller. These are basically temperature controller and current controller. So laser light comes out.
Question.
Yes.
Why do we need a laser controller to control the laser?
So actually, this laser has a semiconductor diode. So they need to stabilize with temperature, right? And also we said we have to send current to it. So any fluctuation in the laser current or in the temperature, that will change the laser frequency. So we have to like stabilize the laser. To stabilize that, we use this controller. To stabilize the current and the temperature, we have to use the laser controller. Yes. So now we can see here. So we can focus on this schematic diagram. So this beam, which is coming out from this laser, it splits into two by this beam splitter, right? So one part of the beam goes in this direction, and it passes through this cesium vapor cell, and that reaches to a photo detector, right? And this photo detector is connected to an oscilloscope. So in our simple absorption experiment, we can use only this beam. So we call this beam as probe beam, right? So in our another experiment, that is saturation absorption spectroscopy, we use two beam, right? So in this case, we actually take this beam, the second beam, so that actually reflects from this mirror, goes to this mirror, again gets reflected from here, and it passes through the cell. But these two beam, this beam we call palm beam. These two beams are in opposite direction. They're moving in opposite direction, right? So this palm beam is much stronger compared to the probe beam. So in our simple absorption spectroscopy, we use only single beam, this probe beam. But in our saturation absorption spectroscopy, we use two beam, right? We unblock this palm beam and we see the spectrum. Now let us move to our experimental setup. So we can focus on the laser source. You can see this is our laser source. So this is our laser source, and we have some control units here. Let's say these are the control units. This is the temperature controller, and this is the current controller.
These are the same controllers.
Same controller that I have
in the schematic diagram.
Yeah. So you see, this is the laser source, and light comes out in this direction. So and it gets reflected from here, and there is a optical isolator that actually.
Okay, so what is an optical isolator? Can you?
Yes, that
elaborate
optical
on that?
isolator actually acts like an one-way bulb. See, it blocks the reflected light, which may damage our laser. So actually,
it only allows one
directional flow
of
light.
the light.
So can you give the start? Okay. Now we can see this the laser. So this is actually having 852 nanometer in the IR range, infrared range. So we cannot see in naked eye. So this is our laser coming here, and we put a beam splitter here to split the beam. So the straight part goes for another purpose, but we take this part for our saturated absorption spectroscopy study today, and this beam actually splits here again, yes, into two. So one part, which you call the probe beam, as I mentioned earlier, that passes through this vapor cell list here. So inside this coil, we have a cylindrical glass cell that contains cesium vapor, right? And behind that, we have a detector.
I see a coil that is wound around that vapor.
Yes, yes. So sometimes we can use like a static magnetic field. So using this coil. So this is a solenoid, right? If you pass current through this, so it will produce a uniform magnetic field, and the direction of the magnetic field will be along the axis. So this magnetic field can tune our transition frequencies. We can tune them to G-magnet. Right.
So is it in use in this experiment?
No, currently we're not using this. So you see, this is the optical path for probe beam, and there is the detector, right? So for palm beam, we have this is the mirror. So we can see, if you see this. So this is our palm beam. In the air cut, you can see this, and this is the mirror. It reflects the beam, and we have blocked. Currently, we have blocked the palm beam, right? We have put a blanket to block this. So
can you show again the path of the probe beam that is getting
so yes. So this is the probe beam. You can see it is very faint.
It's very faint.
Faint, yes. And the palm beam goes this way. So it actually we split the beam here, and gets reflected from this mirror, and we can see it's strong, right? This is the palm beam. So currently we
You have a special card that allows us to see infrared light.
Yes. So this card actually, this card actually converts the IR frequency to like visible.
Okay, so you can see the
frequency.
spot on.
Yes. So now we are ready to see the spectrum with the palm beam only. So now we can focus on the oscilloscope to see the spectrum. So this you can see this red line. So this corresponds to the change in laser frequency. So we are actually scanning our laser frequency from low to high or high to low, from this point to this point in this range, right? And this blue signal is the signal that is collected from the photodiode that is placed here. So when we are, yes,
I have a question.
Yes.
This yellow signal,
yes,
what is it? Okay, so what is it doing actually? Is it connected to the laser source that we are using?
yes, it is connected to the laser source, and we have a controller, and that actually changes the laser frequency in that range.
Yeah,
So
that signal is actually
As
responsible
res-
for changing the laser frequency.
yes, yes.
Okay.
So the x-axis is like it's connected to the change in the laser frequency. We're scanning in this range. So now, if we see the spectrum, this is the intensity that is collected by the photodetector. So at this point, we can see here. So at this point, so this is close to the transition frequency. So at this point, what happens? The cesium vapor, the cesium atom inside the cell, they actually absorb light from this laser and go to the excited state, right? And that is why there is a less transmission in the signal, right? In the light. So that is why we see a dip, right?
Oh, so we are measuring the transmission with the photodetector. That's
Yes.
why as the vapors
the-
are absorbing
Absorbing light,
transmission.
yes, there is a less transmission and we get a dip here. But we are not getting a sharp dip, right? So there should be a sharp dip because the transition frequency is so at transmission frequency there should be only absorption, but we are not getting a sharp dip. That is because of the Doppler effect. So now let us understand what is Doppler effect. So if we consider sound wave, so suppose this is a source of sound and this is the observer. So if they have a relative velocity, they are moving to each other, then what will happen? The observer will see higher pitch in the sound. That means the frequency of the sound will appear to be higher to the observer. If the observer moves away from the source, then what will happen? It will the observer will see sound with lower pitch. That means it will see the lower frequency. So similar.
So this is like this ambulance coming to you. It goes
Ambulance coming,
beep, bap, beep, bap.
Yes.
Then when it goes away, it goes beep, bap, beep, bap.
Yes.
Then the sound frequency changes.
Yes.
Okay.
So in this case also, so we are sending the probe beam like this. So some atom can move towards the laser, and so they will see positive like increase in frequency.
Whatever we have learned about Doppler shift in sound, the same thing happens
Same thing
as
happens.
light.
Similar
as
thing
well.
happens.
Okay.
Yeah. So if the atoms move towards the laser, so it will see increase in frequency. So we call it blue shift in case of light. So if the atom moves away from the laser, so then it will see decrease in frequency. Right. That's called red shift. So in the spectrum, now we can focus the spectrum. So when we are not in resonance also, suppose this is our resonance point, this is the resonance frequency. So if we are here, so what is happening? So some atoms actually can move towards the laser, right? They're in thermal motion. So they're moving randomly. So a group of atoms can move towards the laser and they can see blue shift. So still they can be in resonance in this frequency and they will absorb light, and therefore there is some absorption and some amount of decrease in the intensity that is detected by our photodiode.
So we are seeing this broad dip in the absorption and broad signal just because the atoms in the vapor cell are moving randomly.
Moving randomly.
Okay.
Yes.
So all of the atoms having different velocities. And,
Yes.
Okay. So
And that is why yes.
can you tell me what is the distribution of the velocity that they
So
follow?
it follows. So it follows normally. It follows Maxwell Boltzmann distribution.
Okay.
But in one dimension, it is like normal distribution.
Okay.
So,
So these atoms are following Maxwell-Boltzmann distribution. That's why the dip we are seeing is not very narrow.
yes, it's not
broadened.
Yes, it is broadened, and all the real atomic transition that I have shown in the energy level diagram. So there is sub level, right, from ground state to the sub level transition. They are hidden inside this, right? So when we are far from the resonant frequency, like in this area, so almost all the light actually uh, passes through the cell. There is no absorption. So we see there is a huge intensity that is collected by the detector.
We are detecting larger intensities when we are very far away from the resonant frequency.
Yes.
So the transmission increases just because the atoms doesn't absorb them.
Yes. And this broadening, actually Doppler broadening, it is like hundreds of megahertz, and our real transition frequencies, they are inside them, so we cannot see them. So to overcome this Doppler broadening and to see the real atomic transition, so we use saturation absorption spectroscopy. And so in that case,
Is that a special kind of technique?
yeah, it is a special technique. So here we use two beams. One is the probe beam that I'm showing, and the other one is the pump beam. So that I have told you this the another beam which is much stronger. So now we can unblock that. So we can change here and make it clear. Yes. So now I will unblock our palm beam to this.
So okay, until now the one of the beams are blocked.
The palm beam was blocked. Only one beam was there. That is the probe beam.
So we were studying the absorption of only one
only
so
one
far.
beam. So
Okay.
and that is like limited by this Doppler broadening. So now we can unblock the other beam. Now we can see the real transition. So here you can see the sharp feature that are the real transition. So now what is happening now? So now since we are scanning our laser frequency from this point to this point, so it is continuously changing our laser frequency, and we are getting this spectrum. So suppose we are at this frequency. So this is our the transition, one of the transition frequency here. So what is happening? So in this case, at exactly the when our laser is at exactly the transition frequency, then all the atoms which are having motion in the direction of the laser, so they will have Doppler shift. So they will have different frequency. They will see different frequency from the real transition frequency. So they will not have the linear line. But the atoms which are moving in the perpendicular direction, or we can say they are stationary with respect to the laser direction. So they will see the real frequency, the laser frequency, so without any Doppler shift. So now they will be able to absorb this photon from the laser and go to the excited state. So now, since palm beam is much stronger, so palm beam is going this way. This or laser, the silicon particle, palm beam is going this way, and probe beam is going this way. So palm beam will excite them to the upper state, right? So excited state, and this probe beam will be much more transparent because there is not more atom to absorb the probe beam. So all the absorption is saturated by the palm beam. So that is why we see a peak at the resonant frequency. And in this case, so though the probe beam and palm beam are oppositely propagating, like they are moving in the opposite direction. So though these two beams interact with this stationary atom simultaneously, right? And we see this kind of peak. Now can focus on this. Yes. But suppose when our laser is at this point, like not in the in any transition frequency, what happens? So in that case, since our probe beam and palm beam directions of it, so they do not uh, uh, interact with the same group of particles which have same velocity, right? So that is why we see the similar Doppler broadened background, and there is this.
real transition frequency. So now, if we see our energy level diagram, so we can focus on this. So currently we are scanning our laser such a way that we can see the transition from this level to this level. So from our energy level diagram, so our ground state cesium atom can move from this to this one, from this to this one, from this to this one. But this transition is uh, uh, forbidden quantum mechanically. So we can have three peaks. But instead of that,
So why cannot go from this is x is equals to 4
so
to x
yes.
is equals to
So this is forbidden because of selection rule, quantum mechanical.
so this is coming from quantum mechanics.
Yes. So we are getting much more peaks here. So 6 peaks basically. So this extra peaks we have had amplitude. So they are because of we call them
saying that from this energy level diagram,
Yes.
we should have got just the
3 peaks.
three peaks,
But
but here in the signal we are getting six peaks.
6 peaks of the peaks.
So where are these three extra peaks coming?
So okay, these peaks are like this one, this one, and this one, and this one. These peaks are called crossover peaks. So in this case, what happens? Suppose we are here, so halfway between the two real frequencies. So what happens? So there are two groups of atoms which have same velocity but moving in the opposite direction. So so one group can be in resonance with this peak, right? Because of blue shift, and another group can be independent with this frequency because of red shift, right? So that is why two groups participate in the atomic transition, and in this condition, actually probe and pump both uh, uh, interact with these velocity groups, and that is why we see much higher amplitude here.
Okay,
Right.
that's
So
because
now, yes,
more velocity groups participate in those transitions, so the intensity of those peaks are higher.
higher. Yes. So now we have the real atomic transition.
So this is how we can distinguish between the actual transitions and
And
crossover.
Crossover transition. Okay.
So the actual transition will have less intensity
Less
than
intensity,
the crossover.
yes, yes. So now we have these atomic transition frequencies, and we can select one of them, to lock our laser, because our laser is very sensitive to the temperature, current fluctuation, and mechanical vibration. So it may drift from the frequency changes with time. So to lock our laser, we have built inbuilt lock box. So that actually using that we can select one of the transition frequency as latent, and it continuously checks if there is any change in the laser frequency, whether it's like in positive change or negative change, and based on that, it sends the correction signal or feedback signal to our laser, and our laser is in that remains in that reference frequency. So with that, we can stabilize our laser for long time. Right. So and uh, with that, I would like to hand over to Shobto, who will explain the application of this stabilized laser in the
So I am Shatrugata. So now I will explain.
Shraddha, before you do that, there was a question on somebody asking about uncertainty principle on the YouTube. Could you just take that question?
Yeah.
Yeah. So let me just repeat the question for you. The question was whether if you cool atoms, the uncertainty principle becomes important or not. And
So no, it doesn't violate uncertainty principle, because even if you cool to very low temperature, it won't be very stationary. Okay, so the random photon peak from the lasers will always basically keep your atoms moving with a very small velocity. Always. So you cannot like move the atom stationary. So it doesn't actually violate the. I'll explain that actually. So yeah, as Sushant has explained to you, we need to lock the lasers to cool the atom. So there are also two more important elements to cool the atoms and to get this magnetic architecture. So first thing is that we need to lock the lasers, and second thing is that to trap the atoms, we need to have a source of atoms, and also third thing is that we need to cool the atoms before trapping. Okay.
So now we will show this setup actually. So this is the same thing for the cesium. There, Sushant have shown you how to log the lithium laser, how to log the cesium lasers. Now it is for the lithium. Now for lithium, we cannot buy these conventional these vapor cell kind of thing because lithium is highly reactive. Okay, so we have built one vapor cell here. So in this long tube, we have put a chunk of lithium and heat it to a temperature of 300 degrees centigrade. 300 degrees centigrade. So some lithium will be vaporized at this temperature, and yeah, you can also see there are beams which is going to these vapor chambers. Same beam, one is reference and one is pump and probe. So this is used to lock the lithium laser for particular transition for cooling and the trapping. Okay. So after this locking of the laser, we also send this laser via this optical fiber. You can see these blue color things are optical fiber, which carries the light from this table to this table. Okay. So you can see the red light is going to this fiber, and you can also see this is coming out from this fiber. Okay. So this is to carry the light from one table to another table. Okay. So after taking the light in this table, we basically there are multiple optical elements there, which basically to like expand the light beam to a very big beam, and also like maintain the light polarization and divide the beam into the multiple beams for trapping and the cooling. Okay. Now I will come to the first basic point. So we need the atoms for the cooling of the atom and to trap that, right? So we have built one atomic oven in our lab to get the source of the atom. So now I will show the atomic oven. So by the way, this is our whole setup. This is the main section of our where we do all our experiments. And in this section, we have the atomic oven. And by the way, this chamber is maintained at a very high, ultra high vacuum environment. This is, you can see the main section is the pressure of 10 to the minus 11 top. Okay. So for reference, our atmospheric pressure is 760 top. Okay. So this is called ultra high vacuum environment. So now in this section, we have this atomic oven. So in this section also, we take a chunk of lithium and heat it to a high temperature, let's say 300 degrees centigrade, and some lithium will be vaporized. Then we have to also collimate
I have
this.
a question.
Yes.
Okay, so we put solid lithium into this oven, and that is heated up to 300 degrees Celsius. So is there a way to understand if the lithium is completely vaporized or it's still left inside the oven?
Okay, so you can see that by using this mod loading rate, the loading rate of atom in this trap actually.
Okay.
So you can see that with the time the loading rate will be slow. So then you can estimate this lithium atomic vapor rate will go down. So you can refill. You can take it out this section and refill the lithium into this oven.
So if the rate of loading of the lithium signal
Into this,
is faint, then we can understand that
Yes,
there's less lithium in the
keeping all the other parameters fixed. This laser power and keep all the other parameters fixed. If your rate becomes low, then you can this lithium
reload
this lithium into this oven. Okay. So we also have to collimate this lithium beam into this section so that it can go through this tube and go to the main section of the vacuum chamber. So to do that, we actually have slack hypodermic needles in this section, which actually collimate this atomic beam. And now atomic beam will travel through this tube into the main section of the vacuum chamber. Okay. Now, for reference, the velocity of lithium here is like very high, like 1,000 meters per second. So we need to cool the lithium atoms before we trap the lithium atom. So to cool them, we use some technique. It's called the Doppler cooling technique. Now, we can simply explain the Doppler cooling technique by this diagram. Okay. So now consider the atom to be a two-level system. It has a ground state and it has a side state. Now, let's say velocity of the atom is in this direction and the laser is coming from this direction. Now, if we exactly tune the laser to the exactly energy gap between these two levels, the atom will absorb the laser beam So two things will happen after the absorption. The atom will go from ground state to the excited state, and atom will get a momentum kick in the opposite direction. Since the photon carries the momentum. Okay, but it cannot stay into this excited state for indefinite time. So after some couple of nanoseconds, it will come back to the ground state and it will spontaneously emit a photon. It will get again a momentum kick for this spontaneous emission. Okay, but this spontaneous emission is isotropic in space. So in all the direction, it will emit the photon. So if you like get a vector sum of the all spontaneous emitted photon, you will get a 0. So the net momentum kick of the atom is the opposite to the direction of its velocity. So that's how we basically cool the atoms by multiple times absorption and this spontaneous solution, many times actually. So then the atomic velocity will get reduced. Okay. But there is a catch in the whole explanation. So as you know, as Sushant already explained, so there is a Doppler shift in the sound. So if the observer is moving, then it will see the different frequency of the sound, right? So if the atom now, let's say atom has a velocity of 1,000 meters per second at the initial position at the close to the oven. Now after some time, if it gets cold and the velocity will reduce to 800 meters per second, then it will see a different frequency of the laser beam, right? So we have to compensate that. To compensate that, we use some
So you are saying as through this chamber, when the velocity of the atoms keep on reducing, they now, as the velocity is reducing, they are not absorbing the laser.
They won't absorb anymore. So after
Okay.
some time, they won't absorb anymore. Since you tune your laser frequency, so let's say we first tune the laser to the energy gap between the two levels. So after some time, it won't absorb the laser, right?
Okay.
So
as
you have
the velocity is changing. It is also perceiving the laser frequency has to be different.
Yes.
Then
this
true atomic transition.
true atomic transition. Yes, because you know the Doppler effect is same here. So we have to do something to compensate that. To compensate that, we use some technique. So if you put an atom in a magnetic field, this gap between this ground state and excited state can be changed. Now in this diagram, we will show how we basically change the ground state and the excited gap between the ground state and the excited state. So at the very beginning of this cooling cycle, we put a very high magnetic field, and it is slowly basically reducing to small b value. So what it will do actually, so it will tune your the gap between the ground state and the excited state. So initially it will be very high, and also your laser will be blue shifted since it is a very high velocity. So it will absorb the laser beam. So while going in this direction, actually, so the velocity will be reduced, and also your magnetic field will be reduced. So now the gap between these ground state and excited state will be also low. So this atom will on resonance in it all the path actually when going through this atomic Owen section to this main chamber. So the purpose of this thing is to like keep the atoms always on the resonance. Okay. So after that, we basically send the laser beam from the six direction, from this direction, and from top and bottom. Okay. So this six direction, the beams from the six direction, and also there is a magnetic field on the top of the vacuum chamber and also the bottom of the vacuum chamber. So these laser beams and this magnetic field using this coil create a trap of the atoms, which is called the magneto-optical trap. So it will trap the atomic cloud at the center of the vacuum chamber. Okay. So now I will trap the atoms and show you the atomic cloud, the lithium atomic cloud. So this is for the current for the magnetic field. Okay.
So now you are setting up the magnetic field on the chamber.
Yes. So now the magnetic field is on, and so now there's a bulb opening to lithium, so that the lithium beam will go to
So now
that
we are releasing
direction.
the lithium
Lithium
polymetal lithium beam into the.
Yes. Now I'm reducing, and this current is for the demand slower. So to slow down the atom, okay, and And this is to route the lasers through the cap. Now we should able to see this lithium cloud. You can see actually. You, from this direction. So actually, from this window, we can see the atomic cloud. Like this thing through this window. So can you turn off the light? Yes. So there is a dot actually. You can see actually there is a small dot on the center of the vacuum chamber. So this is very difficult to see, I think, in the cameras. We will show in this. We have a video of this atomic cloud, so we will show actually in the video. Okay. Here. So, so the first you can see the cloud at the center of the vacuum chamber. Then I will turn off this magnetic field. Now there is no cloud. Then I will turn it on again. So now you can see the cloud is expanding actually. Not sure.
Share both and both. We are seeing it from the.
Okay. So now I'm showing it again actually. So now you can see the lithium atomic cloud. All the things are on. So now it is off. Magnetic field is off. Now I will turn it on again. Now you can see this atomic cloud expanded inside. Slowly the atoms are getting trapped and it will form the atomic cloud. Okay. Now it's off sharing.
Yes, still the share.
Now it is sharing. Share the light.
Soon. And switch on the light. Yes, I did. We're going to conclude.
So now, after trapping the cold atomic cloud also, we trap the ions at the center of the vacuum chamber also. So how to trap the ions inside this vacuum chamber? So we use this kind of trap, which is placed at the center of the vacuum chamber. This is called a fault trap. We apply RF voltage into this core rod and also DC voltage into this end cap. These are called the end cap. There are two end caps. We apply DC voltage into the end cap. So after trapping this atomic cloud, actually, we shine a laser light to controllably ionize some portion of the atom, and they will become the ion. So then we'll turn on this RF voltage and this end cap voltages. Then these atoms will be trapped. These ions will be trapped at the center of the vacuum chamber also with the atoms. So now these ions cannot be laser cooled. These are non-laser coolable ions. So how to see the ions? So to see the ions, we use some technique. So we use some detector which is called the CEM. So So how to detect the ions in the CEM? So as I have told you, we apply DC voltage into this end cap. So let's say we apply 40 volt into this end cap. So initially, this end cap is also at 40 and this is also at 40. Now, suddenly, if you turn up one of the end caps to minus 10 volt, so now this end cap will at 40 and it is at minus 10 volt. So ions will feel a potential gradient in this direction. So it will extract out from the whole of this ion trap and hit a detector here, which is called CEM. And we can see peaks on the oscilloscope for each ion. So here we have a picture, magnified spectrum for lithium and lithium. You can see here. So this is the spectrum from the oscilloscope. This is for the lithium. Since the lithium is heavy, it will arrive first. And since the cesium is high, the cesium mass of the cesium is high, it will arrive later. So this is the time of flight spectrum.
Okay, so the CEM, what does it stand for? Two questions.
Channel electron multiplier.
What does it stand for, and does it measure the number of
Yes, yes.
atoms
So
that
each peak is a number. Each peak is ion basically. So you can count the number of ions at any given time inside this ion trap. Okay. So yeah. So what we do actually with this core trapping of cold atom and ion? To study sympathetic cooling. One of the goal is to study sympathetic cooling. Since these ions cannot be laser cooled, we cool the ions using this cold atom. So what is happening there actually? So we basically trap these cold atoms and the ions together at the center of the vacuum chamber. So there will be collision between this cold atom and the ions. So that will eventually cool the ions to a very low temperature, and the lifetime of the ions will be very high. So this sympathetic cooling we study extensively in this chamber. So, and we have seen that we can trap this ion beyond 6 hours. Uh, and so what actually people do also with this cold atoms and the ions. So people do one of the hot fields right now in this quantum computing is in the cold atoms and the ions. And also people do all kind of quantum sensing, quantum simulations, and all the fancy stuff using this cold atoms and the ions. Now I will hand it over to Rahul. Rahul will explain how to trap trap nanoparticles. So now, Rahul.
Hi, I'm Ram Mohanty. So I work on optical tweeter, and I'm specifically interested in trapping particles, trapping nanoparticles in air, medium, and vacuum. Uh, the let's have a, and I will share a slide where I will explain how the field started, and later I will demonstrate a short experiment how a trapped particle in air, medium just looks like. Yes, very visible to you. So he's after asking who is the pioneer of this work. So first dropped microparticles in liquid medium. And later, 1 year later, he dropped microparticle in air medium, where he trapped it using providing a vertically upward, a laser beam which was moving vertically upward in vertically upward direction. So let's have a look experimentally at how a trapped particle in air medium look like. So can you switch up the light? To stop the screen. Huh. So you can see, is there any particle there? No. Do we have to try a lot of time? Yeah, you can see there is a particle there. Yeah, is it visible to you? Okay, in the camera it is difficult. I can share your video. Yes, you can see. You can see there is a white dot which is levitated in here. Yeah, this is the particle. So
I have a question here. Okay, so from that objective, the light is traveling into, let's say, in the left direction. Okay, so the light is applying a force in the left direction, and the gravity is pointing downwards. So then, how is the particle trapped there? There is clearly a net force on the particle, but it's still levitated in the air. Can you explain that part?
So, yeah, nice question. So here the laser beam is propagating in horizontal direction, but the particle is getting trapped, though there is a
Gravitational force. Yes.
What is happening here? Like there is a harmonic oscillator kind of potential is creating when we are focusing the light, and that is a three-dimensional harmonic oscillator kind of potential.
Okay.
And the force is towards the focus only from every direction. So there is although there is a net gravitational force on it, but the optical force is very large as compared to it. So let's say for a number, if the gravitational force is of the order of attonewton, and this optical force is of the order of piconewton. So it's quite large as compared to that. That's why this particle is getting trapped.
So you are saying that the focused laser light is responsible for creating a harmonic oscillator potential?
Yeah.
In 3 dimensions. That is what is trapping the particle against the gravity.
Yeah. That is particle. We're trapping the particle against the gravity. So it's quite easier to trap the particle in air medium and liquid medium because this medium is providing damping to the trapped particle. But when it comes to vacuum, like there is no damping mechanism, so it's quite harder to trap the particle there. In our experiment, normally how we launch our particle, we use silicon nanoparticle having diameter of 100 nanometer, and those are spherical, and those nanoparticles are dispersed in this ethanol and DI water inside this nebulizer chamber. So when we press the switch, then you can see the aerosols are generated, and the solution is prepared in such a way. It's visible now. These aerosols are generated, and the solution is prepared in such a way that each aerosol will contain one particle or no particle. So when it traverses through this focal region of this laser, then the particle will get trapped. And how it gets trapped, let's look it in an animation. If there is a bead which was located at off center, then
This bead here is representing the nanoparticle.
the nanoparticle, and it is getting trapped at this focus of the laser beam. Let's understand what is the physics behind this trapping. So we all know a dipole is created by two equal and opposite charges separated by some distance. So separated by some distance, when a dipole is presented in a homogeneous electric field, then what happens? It will experience only a torque. But when it is present in an inhomogeneous electric field, along with the torque, it will experience a translational force, and that translational force will drive the dipole.
Yeah, I have a question here. So, by homogeneous and inhomogeneous, what do you mean? I mean, they are varying in inhomogeneous field is varying in time domain or space domain.
So inhomogeneous means if I am present here, if I am standing here, the electric field value which I am experiencing, now I will go to your plane, the electric field value I will experience will be the same. So over the space, the electric field magnitude will not change. But if it is changing, then it will create an inhomogeneous electric field. How we can create it by the laser? Then we can focus it so that it will create a tiny spot. In that case, we can create inhomogeneous electric field. Before the lens, we can see here that the laser beams are parallel and its diameter is not changing, and as power of the beam is also not changing. So we can say the intensity is remaining constant. So intensity is proportional to I by A. So the the power is proportional to I by A. So as power is remaining constant and area is not changing, so intensity is also not changing, and intensity is proportional to electric field mod square. So the electric field is also not changing. But when we are focusing the laser beam, then it is going to a tiny spot where the area of the beam is getting reduced. And in that case, as the power is remaining constant, the intensity is increasing. As intensity is increasing, the electric field value is also increasing. And that higher electric field value will attract the particle towards it. And whenever it will try to go out of that region, again it will come towards it. So we can say focus laser beam is creating a harmonic oscillator potential well, and the particle is moving inside it. Here is a result where we can see that the left side, the top left side picture is showing that how a particle is moving along x direction in this harmonic oscillator potential well. And this data is taken at 50 torr, where the atmospheric pressure is 760 torr. So, and the right side is the corresponding frequency domain picture. We can see that the frequency domain picture is quite broad, and that broadness is because this particle which is moving inside the harmonic oscillator potential well is constantly getting kick from the surrounding gas molecule, for which its harmonic oscillatory motion is not quite prominent. But as we are reducing the pressure in the chamber, where the pressure is 8.6 into 10 to the minus 1 torr, we can see a clear peak in the frequency domain picture.
So by reducing the pressure in the chamber, you mean by reducing the number of gas particles that are inside the chamber?
Yeah, the sum. We are evacuating the chamber with the surrounding gas molecule. We are extracting.
Okay.
In the pump. So, but if after that, if we will continue to evacuate a chamber, what will happen? The particle will enter into the ballistic regime, and its oscillation amplitude will increase, and it will get out of the trap. So we have to implement a feedback mechanism to keep the particle trapped inside this potential well and to reduce its amplitude of oscillation of motion. How we will do that? And that I will show in this next animation. So a particle you can see is located at the center of the potential well, and we are oscillating the laser beam which is trapping the particle at twice the oscillation frequency of the particle. And the feedback is to go in a correct phase so that the cooling will occur. Otherwise, it will lead to heating. I'm starting the animation, you can see it here. So see, at this phase, the amplitude of oscillation of the particle is small. And if the phase will change, then it will lead to increase of oscillation of the amplitude of the particle, and that we call heat. So in our experiment, we have implemented this parametric feedback cooling. And after implementing parametric feedback cooling, we have cooled the motion of the levitated nanoparticle up to some extent, where you can see this is the data of before implementing parametric feedback cooling, and after implementing parametric feedback cooling, we can see clearly the peak height has been reduced and the area of the cloud has been. So that implies the particle is getting cooled, but we are trying to cool it further down. So, but there is an open question here, like there are two temperatures in this nanoparticle, and it is a solid system. What we are trying to cool right now is a center of mass temperature, but there is atoms and electrons inside this nanoparticle, which gives rise to its internal temperature. Though the center of mass has been cooled to several hundreds of microkelvin or tens of microkelvin, still its internal temperature is very high, and it can be cooled. Its internal temperature can be cooled if we can keep it in contact with a cold object. Like in our case, we are planning to keep it in contact with cold atoms, so that its internal temperature will also get reduced. And that's my what.
But I have a question.
Yeah.
So why do we have to cool nanoparticles? What are we trying to probe by cooling nanoparticles?
Okay, yeah, that's a nice question.
Hmm.
So, as we all know, in electron, when we will pass it through a slit, we can see the position probability density in the screen behind it.
Hmm.
And what is the reason behind that? Like the de Broglie wavelength of the electron is of the order of the slit width of the slit width through which it passes through. But what happens when we will pass the nanoparticle, like in our case, the 100 nanometer nanoparticle, through the same slit, having same width? So can we see the same superposition as we get in case of electron? No. So because the de Broglie wavelength of the nanoparticle is quite smaller as compared to the slit. So we have to cool the nanoparticle so that its de Broglie wavelength expands, and if we can prepare a slit of that width, then we can probe its quantum nature, where I am saying the quantum nature means the probability density of the nanoparticle.
And so by cooling means arresting the momentum of the nanoparticle.
In the momentum.
So if the momentum reduces, the velocity also reduces.
Yeah.
And so it increases the de Broglie wavelength.
Yeah.
Okay.
Yeah.
The nanoparticle.
Yeah. This is still an open question. Okay.
Can stop the screenshot.
Okay, so that was fun. Certainly, you guys are doing some very interesting stuff with these cooled atoms. So one of the questions that were asked is, what are these atoms? Why do you want to cool stuff? So what do you do with the cold atoms? So you want to just say what all things you can do with cold atoms? Or we can get Saurav into the picture as well. Come on, join us. So one of the things that was asked, of course, I see that there's lots of very great cool experiments happening. So one of the things that were asked is, what do you do with these cold atoms? I mean, what do people do with them? Why do we study cold atoms? What are they useful for? So do you want to comment something on that? Because that's one of the questions that we asked on YouTube.
Yeah. So, so this this is not a very new field. It's relatively young compared to other fields. So initially, people basically wanted to get things cold so that they can do what earlier people thought as hot experiments. You can actually with cold atoms look at single atoms, for example, and you can do mirror. For example, initially people saw what known as quantum jump. So actually, when the atom hits the transition from one to another, or comes down, it hits one. You can actually you need to have one atom. So these are kind of thought experiments which are not possible now. Meaning 30 years it's possible. So these are very fundamental things that atoms are actually quantum objects. So this is what started, but then slowly it moved to once people understood the single particle physics is actually more or less a very quantum mechanics. They moved into more number of particles, and the idea was that what happens when you bring particles together, so things start to interact, and then there were these condensate, those condensate forms. So they are macro like 10 to the power 4 or 5 atoms which collectively behave at a single wave. And of course, one of the things also which motivated the field is to do something in between. This is a mesoscopic physics. It's difficult to study, but here you can have 100 atoms. So fundamental things interaction. Also, it has actually boosted our you need to do very precise measurement. Like, typically, when you do measurements, we typically measure frequency because that's the most accurately measured. And so these are applications in clock. So atomic clock, it gives our time, GPS, that gives us that precise positions is actually dependent on having very good clock. So, so atomic clock is one thing. So right now, for example, we cesium atoms are used as clocks, and these are done on the microwave transitions, which which my students probably showed you the ground to ground levels at the time. But now, in the next, maybe in the next 10 years, it will probably become optical clocks. We have to use optical transitions in different atoms, function or even trapped ions, where you do optical clocks, and they have much better stability. So these are stabilities of 10 to the power minus 18, which means that if you wait for 10 to the power 18 seconds, which is more than the time the universe typically was born, you will lose only 1 second. So they are very precise things. So clocks are a very big application. And then you can do sensing. For example, you can measure magnetic fields very accurately at levels of even femtotesla per square root of Earth. So these are applications. For example, you can do atomic magnetometers, which you can put in a helmet and put around the head and do actually scans like an MRI scan, but without applying this large magnetic field. So you are actually in a zero magnetic field environment where you can detect signals from brain, from the heart. So this is one application, but these people also want to do it also for fundamental things. So these very precise magnetometers, there are networks of this, and people know sort of what to expect out of what reading to expect. And the idea is that if there is a network of magnetometers and if everybody sees an anomaly, which at the same time or with a correlated thing, then they should be able to say that there's something which was not expected with thing, which sort of hints towards some kind of an physics. So this is also another thing by people research. And then there is there is use in which is very in the news now. It's trying to do quantum computing. Right?
Okay, yes. Everyone wants to do quantum
Yeah, with atoms and ions. So there actually ions were for a very long time. So ions were the first to be laser cooled actually before atoms in 1980. And they can be trapped in a very deep trap. So they can live for very long. So they have been for the last, I think, almost 25-30 years, people have been thinking about using ions as qubits. So single ions trap where you can image them and get nice images, address them and use them as qubits and do quantum computing. And then now even atoms can do it. So for a long time, the problem with the atoms was that atoms do not have a charge, so you cannot trap them for very long. So, but around around 2010 or 12, people started realizing that you can actually do these optical tweezers, focus them down very tightly and trap atoms there, and you can make an array of them. And if you can do the computation very fast, and then you can use the Rydberg states of atoms to do quantum computing. So in the last 10 years, actually, neutral atom-based quantum computer has almost become comparable to trapped ions, and which is sort of similar superconducting qubit quantum computing. So there is a lot of interest in.
Great. Thanks. Okay, let's just check if there are any other questions on YouTube. I don't think so. We've answered a couple of them online anyway. And if you have questions, remember you can always write to us, outreach, outreach, outreach@tifr.res.in, and we will forward your questions to the team and hopefully they will get back to you. So on that note, let's end this session with a reminder that our next Chai and Why, 6th of September, is going to be on physics of the plug point at Prithvi Theatre. And before that, of course, tomorrow afternoon, there is a special colloquium by the CERN Director General, which is open to the public on particle physics today and tomorrow, followed by a special film screening of the film called The Peace Particle by CERN, which highlights its 70-year history of being a center for international collaboration. So on that note, thanks for watching, and keep coming to Chai and Why and watching us online. Thank you very much.
Yeah, this is cool.
Is there anything that you wanted to show? Did we miss something?
Everybody So maybe
Yeah, maybe we can say we can just have all of you guys together and yeah, and okay. So I'd like to thank everyone in the lab. Thank
And our
you all
camera
for
man
thing, and of course there is Rahman whom you don't see because he's behind the camera, but he's been the one trying to make sure that we could see whatever we could see. And of course, with all this dense part of optical components, it's very difficult to look inside the system and see the cold atoms, and hopefully you will see it on the video. So on that note, thanks a lot, and thank you for showing your lab, and thank you all for watching.